Okay, good afternoon. So two announcements. First, tomorrow there'll be a makeup session. So during the makeup session time, there'll be a lecture. There might be a tutorial as well in the morning at 9. That I haven't yet finalized, so I'm going to talk to Arvind and see if he will be available to give that tutorial. If not, we'll have to just post a pre-recorded tutorial for lab 2 because we can't really have tutorials during the midterm week, and after that during the reading week. So just please read the lab manual, and if you are planning on attending a tutorial, if there is one, for now there is no guarantee that there would be one, but if there is one, come there with questions that you might have. Okay, so these are the two. Now let's get started. So just a recap on where we are in the course. So we talked about the operating system concepts. We talked about implementing threads and providing support for synchronization. So that was kind of like the first part of the course. Then we started talking about scheduling. So this is basically the second part of the course, CPU scheduling. We talked about uniprocessor scheduling, and we went through 7 or 8 different types of scheduling, or 7 or 8 different scheduling policies. Now, in today's lecture, and probably half of next lecture, we are going to look at multiprocessors. Now, we're going to look at multiprocessors in not just for scheduling, but just to understand how they're different from uniprocessors. And at the end of these lectures, we're going to touch upon some of the important aspects of scheduling when it comes to multiprocessors. So with that introduction, let's start. So we're going to talk a little bit about multiprocessors, just introducing them as needed. So in terms of hardware and how it's different. Then we will talk about multi-threading on multiprocessors, because most of our focus so far has been on multi-threading in a uniprocessor. So we're going to see how moving to multiprocessors is going to make things different. So then we'll talk about load balancing in a multiprocessor, and that would be a segue to talk a little bit about scheduling policies for multi-threaded programs in a multiprocessor. Okay, so the first thing to mention about multiprocessors and the grand view of scheduling them is that we have a simple goal. We have a simple objective that is true for uniprocessor and multiprocessor, and that is, if you have a CPU that is available, and if you have a thread or a process or a task that is ready, then you better run it on your CPU. And you know, this is in a context of work conserving schedulers. So if you have a CPU and you have a task to do, then do it. Don't wait. Now we'll see that implementing this very simple invariant, or this very simple goal, is going to be hard in multiprocessors. It's going to be a lot harder than doing it in a uniprocessor. So a little bit of background on multiprocessors. The first aspect of multiprocessors that make things challenging is heterogeneity. Now, you might have multiprocessors that are homogeneous in terms of CPUs. All CPUs might be the same, but also you end up in your career probably dealing with multiprocessors that are not homogeneous. So if you're working with Android operating systems, for example, or any mobile operating system, then you probably know that many of our cell phones and our maybe tablets, they have heterogeneity inside them. So there are powerful CPUs in our cell phones, and there are basically low power CPUs. Now, powerful CPUs could be used whenever we have an application that requires performance, and low power processors could be used whenever we want to save power, avoid our cell phone to get hot, or we want to let the processor to cool down. Now, this creates asymmetric environment. So when you have different types of processors that are good for different tasks. So one of them might be good for performance, but not good for power. And the other one might be really good for power, but not that good for performance. Then the question becomes, how do you schedule your applications on these processors? Now, you probably would want to, give the powerful processor to applications that need processing or compute that have computing needs, and then schedule for example your background applications on the CPUs that provide low power. So this is very famously done, these kind of architectures on ARM big little architecture, which for a while was basically the golden standard in our mobile processors. And this is actually finding place in high performance computing as well. So with this explosion of a specialized hardware, we're going towards the situation where we have, like for example, these TPUs, the Google TensorFlow processors. They're very power efficient, and they're very good at doing matrix multiplication, for example. And then you have these general purpose CPUs that are good for any general purpose job. And now you want to make a decision who runs on the TPUs, what portion of the application runs on the TPU, what portion of the application should run on the CPU, how should they communicate, how the resources should be divided between these. And this is an aspect that is challenging, and it's getting a lot of traction in research. The other aspect of multiprocessors that make scheduling them and basically managing resources in them hard is the non-uniform memory accesses that exist in multiprocessors. So what is that? So with uniform memory access or UMA, you have a single memory controller that is connected to all your CPUs and connected to all your memory banks. And every time a CPU needs a memory load or store or any kind of computation on memory, the request is sent to the memory controller, and from memory controller to the corresponding bank. Now, it doesn't matter if the data you want resides on this memory bank or on this memory. The time it takes for any of these CPUs to access any data is uniform. It takes the same amount of time. Now compare that with non-uniform memory accesses. In this one, we have different memory controllers for different memory banks, and some of the, or at least one of the memory controllers is local to each CPU, and the other ones are remote. Now, if you are CPU1 and you wanted data that resides in this bank, this is going to be considered a local access, so it's going to take a lot shorter than if you want a data in this memory, which would require a remote access. So you need to send a request to this other processor, or basically make it be delivered to this memory controller, and this memory controller get the result and then sends it back to you. And this is going to take a lot longer than if you wanted to talk to the local memory controller to yourself. Now, so this is the introduction of numa, and we'll see that this is going to be making the job of us scheduling tasks a lot harder. Just to give you an idea, for example, if CPU1 was running T1, let's say task 1 or thread 1, then the data for T1 is probably here in this memory. Now, if for whatever reason T1 is migrated to CPU2, now we have two options: either go with remote memory accesses to get T1's data, and you can see that this could be really expensive, or just undergo this data migration as well. So migrate the data for T1 so that our memory accesses are local. So making this decision, when to migrate, how to migrate, do I actually want to migrate T1? Should I stay where I was? This is going to be a matter of discussion that we will discuss when we talk about load balancing at the end of these lectures. That would really depend on this numa architecture. Okay, the other aspect of multiprocessors that make things a little bit complicated is the hash hierarchy. Is the cache hierarchy of multiprocessors. So this is what you usually have in your multiprocessors. So each processor, each CPU has its own private cache. And this could be multiple levels of caching. So in this particular example, I have level 1 cache that is private to CPU1 and level 2 cache that is private. This basically means that only CPU 0 has access to this L1 cache, and only CPU 0 has access to this L2 cache. But this L3 cache is shared between all CPUs. So all of them can actually access this. So somebody is asking, is migrating, quote, moving or copying? In the case of data, migrating data basically means copying data from one memory location to another memory location. In terms of tasks, by migrating, I just mean that I was running the code of T1 on CPU1. Now I want to run the code of T1 on CPU2. So this is what migration of tasks, but migration of data basically means copying or maybe moving the data. It matter. It's a matter of implementation. You want to move the data completely, or do you want to make a copy of it? And depending on depending on the application, both could be viable. For example, if your threads, all they're doing is reading data, then you can copy the data. You can have multiple copies of the data on different numa nodes so that everybody is reading. But if one of them is writing, then having copies is going to be complicated, because if somebody writes, then you have to update other data as well. So maybe in that case, you just want to move it. Okay, so going back to the cache hierarchy that we were talking. Now, this is, you might think that this is benign. Okay, so what? Each CPU has its own private cache, and they all share last level cache, and then they all share memory. So why is this an issue? So before talking about the issue, this is how it looks in a modern, I mean, you might say this is no longer a state of the art, but this is from probably 2016 or 2017. So these are the CPUs in the case that in the other figure, and each one of them is going to have its own cache that we don't that is inside this package, and then here are the last level caches that are shared between all CPUs, and then eventually you go to memory here. So this data in a bus is shared between all CPUs, so they can all access this last level cache. And if the data is not there, then they go to memory. Okay, now let's talk about cache coherency problem. Here is a scenario. Let's say that thread A modifies data inside its critical section while it holds a mutex, and then it unlocks the mutex. And then thread B locks the mutex and reads the data. So very a normal situation that we had before, right? You have the mutex, you lock it, you change the data, you unlock it, and then another thread accesses the data. Now let's run this on a multiprocessor with private caches. See what happens. We will see that if all the accesses that thread A had in reading and writing were to be sent directly to memory, we would be fine. And that's what we have been assuming so far, that everything is sent to memory. So then there's this memory that is shared between all threads or CPUs. When I read, I go there. When I write, I go there. When another CPU reads and writes, it goes there. So, and we know how to deal with it, right? We know we can have locks, mutexes, semaphores, condition variables for exact same thing. But as you will see, this was kind of like an illusion. We never really actually go to memory directly. We always go to these private caches first. And then if we can't find the data, then we go to the next level, which could be still private. And if we can't find it there, we go to the next level, which might be shared. And eventually we go to memory. So we go through this cache hierarchy before eventually we end up going to memory. And let's see how that could be causing us problems. So here is the example. So I assume that there is only one level of private caches. There could be multiple levels of private caches, but in this example, CPU A has its own private cache, CPU B has its own private cache, and then I'm connecting them directly afterwards to memory. So I don't put any shared cache. Let's say that each one of them has a private cache and then they go to memory. Let's run the example. So let's say there was this memory location in memory. Let's say CPU B first loaded this. This has come now to the private cache of CPU B. We cache the data so that next time that we access it, it's fast. So after we execute this load, we can expect a copy of the data to be in our cache for the next time so that this access is fast. Now let's say simultaneously now CPU A is running a code that needs this data. So let's say we do the same thing in CPU A. We load this data. And then we actually modify it in CPU1. So we modify this location, and the modification then is saved to this location. Now, when you save it, usually what happens is that you save it in your private cache, and this will eventually be written to memory, but not necessarily right after you write to it. So there we have the data that is written, saved in private cache of CPU A. Now, let's say if now CPU B wants to execute this line again, what should happen? In reality, we should look at this, but unfortunately, this is in the private cache of CPU A, so it's not possible for CPU B to look at it. So if CPU B that goes and looks at this data, this is a wrong data. The actual data now is this one. So we need a way to come and tell CPU B that this data is no longer valid for you. So somehow we should tell CPU B after this store happens that you have to invalidate your cache. You cannot think that this value is valid anymore, and you need to somehow, if CPU B wants that data, so if CPU B says, okay, now give me the latest version, you need a way to put this data back here and then load it here for CPU B. So we need extra steps to make these caches coherent, because they might not be coherent, as you can see in this example. One of them might have the up-to-date data, the other one might have an old data that needs to be invalidated. So this is a topic that people study in computer architecture. So if you end up taking advanced courses in computer architecture, you probably will see this. Where I was studying my PhD, it wasn't even in advanced computer architecture, it was in advanced computer architecture. So we had advanced computer architecture 1 and then advanced computer architecture 2. Yeah, in advanced computer architecture 2, half of the class was about cache coherency, cache coherent protocols. So I'm not expecting you to understand the entirety of these protocols, and you shouldn't expect me to dive deep into these. These are advanced topics. I'm going to just scratch the surface, tell you or give you a flavor of what cache coherence protocol might do. So big picture is that any protocol that wants to keep caches coherent has to implement two invariants. The first one is that you need a single writer and you could have multiple readers. So this is very similar to that lock that we talked. So as long as everybody is reading, it's fine to have multiple copies of the data, and you can have simultaneously multiple CPUs accessing the data if they all want to just read. But the moment one of them wants to write, then everybody else should stop using that memory, which makes sense, right? Exactly the example that we said. So we need to have a mechanism that ensures that either everybody is reading or just one CPU is writing. So this is the first invariant we need to have. So at any given time, I'm either having a single writer or I have multiple readers, and nothing in between. The second thing that we need, any cache coherence protocol needs to have, is that when a load is issued, when a CPU wants to read something, they have to get the most up-to-date version of that data. So that's basically what coherency means. So it means that you shouldn't get an old data. If the data has been updated, you have to get that update. Now, this leads to division in time for cache coherence protocols. So basically, we're going to divide time into events, and the events that we care about are these load and stores. So as long as I have only reads or read requests coming from different CPUs, I can have a read-only interval. So, you know, if everybody is just reading, if I'm just receiving read requests, then I'm fine. So this could be a read-only phase. The moment I receive a write request, the moment somebody wants to write, I transition to an interval that is a write that has a single writer. So in this particular example, at the beginning, A and B were reading, so I had a read-only interval. Then CPU2 issued a write. Now I start a write-read interval, but just for CPU-C, nobody else can have access. And during this interval, CPU-C might change the value of this memory that I care about. Now, at the end, let's say somebody now again issues a read, and I want to open a new read-only interval. The value that everybody should now see should be the value, the last value that CPU-C wrote in this address. So the division of time into these intervals, where I have either readers or a single writer, was the first objective, or the first invariant that we had to implement. And the second one was this one, where you should read the final result of the writer. So as long as your protocol gives me these two, I'm happy. You have implemented a cache coherence protocol. So that's the requirement for any protocol that wants to do that does the job. Now, there are so many different protocols, and they have trade-offs. So one of them is good in something, the other one is good in something else. We're going to look at, high level, what is required of them to have. So I told you already about the objectives that we need, or the invariants that we have to implement. Now, again, high level, to implement this, what do we really require? So I'm going to talk about that. Now, this is going to be general. You might find a cache coherence protocol that doesn't use everything that I'm talking about here. It might be a specific. That's fine. I'm going to just give you a high level approach if you were to implement such protocols. So again, high level, you want each memory address to have a state. So you want to define a state for each memory location. Now, what is that state? This state, again, high level, should be either valid. So sorry, you first want to talk about the validity of this location, this memory. So it's either valid or invalid. Note that we're talking about a memory location that is cached in your CPU. So we're now talking about a specific address, but we're looking at it inside the cache for each CPU. Now, going back to the example that we had at the beginning of the class, So we had this example where A wrote in its own cache and then B wanted to read from its cache. So the cache for B is now invalid, right? That's the validity that we're talking about. So your memory in cache is either valid or invalid. The other thing that we want to have for that is dirty or not dirty. So when you write to an address and you write it in your cache, you make that cache block dirty because you now have written something to it. Whereas if you just read, then it's clean. So it hasn't become dirty. So the dirty state changes if you write. Otherwise, it's clean. The other one is exclusivity. Now, when you cache something in your cache, when a memory block is in your cache, you might have exclusive access to it, or you might have non-exclusive access to it. So for example, if everybody is reading, nobody has exclusive access. If you're the only writer, then probably you have exclusive access. So somebody is asking, who manages these cache coherence states? Right, so I'll talk about it. So the cache coherency protocol or cache coherent protocol is in charge of changing these states. We'll talk about that. So let me first talk about these states, and then we'll talk about how we can use them. Then there is the ownership. So either you're the owner or you're not the owner. And it's different from exclusivity. You might have exclusive access to the memory, but not be the owner of that memory. And lastly, it's permission. Do you have read-only access to this memory, or do you have read and write access to this cache location? Cache block, sorry. Memory location cache block. Okay, so given those states, let's define common 5 states in cache coherent protocols. It's called modify, owned, exclusive, shared, invalid. So MOESI. These are commonly used states in cache coherence protocols. Now, I'm putting them all together. They have some relationship with each other. So the first one is validity. So you have invalid sitting here alone, and all the other states here, O, M, E, and S, are valid. So if you have a memory block in your cache and its state is owned, or its state is modified, or its state is exclusive, or its state is shared, it has to be valid. Okay, so that's the first. Then it's ownership. Now, if you have a memory and you have exclusive access to it, you have it in modified, or you have it in O state, then this indicates ownership. But if you have it in shared, if the state is shared, then you don't own that memory. Oh, I made a mistake. I think here I said you might have a memory in exclusive access, exclusive mode, but you might not be the owner. I messed it up. You might have a memory in ownership state, but you might not have exclusive access to it. So excuse me. So if you have it in exclusive, then you're owner. But if you have it in owner, you might not have exclusive access to it. Then in O and M, the memory could be dirty. You can write to it if you have your owner, or if you have it in modified state, then you could write to it, so it could become dirty. And that's pretty much it. So these are the relationships between different states. And exclusivity comes in E and O. So sorry, E and M. Whenever you modify you have to have exclusive access. So E and M, you have exclusive access to it. You could be owner but not have exclusive access. So you could be owner and yeah, not have the exclusivity there. Now, let's look at a so different protocols use different sets of these states. Not all protocols use all these states, and which states they use usually is an indicator of that protocol. For example, we have MSI or MESI or MOSI or MOESI. So each one of these indicate a different protocol. So the MESI protocol uses MESI states, and just with those states, it can implement cache coherency. The MSI protocol only uses 3 states, and with these 3 states, it's able to implement those 2 invariants. So to implement those 2 invariants, you don't necessarily need to have all 5 states. As you can see, you can just use a subset of these and still be able to implement those invariants. Now, this one uses all 5 of them, but then this one only uses 3 and still able to do what it takes. Now, I talked about the states. Now, let's look at cache coherency in practice. Where does it get involved in the computation that I do in my system? Where is cache coherent protocol invoked or gets to interact with my program? So let's look at it. Let's say that your CPU issues a load or a store or one of those load modify store operations. So any operation that has to go to memory. So your CPU issues that. That's going to go and be delivered to your cache controller. Now, your cache controller then is going to issue a coherence request. So that's where cache coherency is going to kick in. So depending on the protocol, your cache controller is going to issue the request in that protocol, whatever operations that are available. So then, excuse me, then cache coherency is going to respond with the data, and then your cache controller is going to give the data to the CPU. Now, inside here, your cache controller is going to keep the states that we talked about every block of cache that you have in your cache. So for each one of them, your cache controller is going to keep a state. And depending on that state, these requests and responses differ, and that depends again on the cache coherency protocol. Okay, so this is how it's interacting with us. So far, if you go back, everything we talked about, we kind of hid all of this. We never talked about cache coherency. We were always going, a load would always go to memory directly, but in reality, if you have a multiprocessor and processors have cache, then this is what happens under the hood. So you're not going to send your request directly to memory. Your request is going to first go to your cache controller and then be translated to the language of that cache coherency protocol that exists on your system. And then it's going to communicate with other cache controllers and probably the memory to give you the data that you want. So a single load might end up creating a sequence of cache coherency requests. and responses. Now, in line with what I said about those states, oh, I got a question. So how can the cache block be read-only, but still dirty? I thought dirty was if a CPU writes to a value in its local cache. So I don't know how you got that idea that if so, I'm not quite sure. Yeah, can you elaborate on this question? What do you exactly mean? That where did you get this idea that a cache is read-only but still dirty? Okay, so the other question is, what is interconnect network? So this basically is a because in your system you have other CPUs and they have their own cache controller. And they all are interconnected. So they're all connected to each other. So I'm calling that whole thing as an interconnect network. So this is a network that connects all these caches together. And probably you go to another shared level cache controller, and then you go to memory. Oh, okay. So it was apparently it was resolved, the previous question. Okay. So that's that. Now, depending on the state, you might. So I said that the CPU issues load and store, and then the cache controller starts issuing cache coherency requests. Now, what are those requests? So these are the examples that could happen. So, for example, your cache controller could ask the coherency protocol to get access to this memory block in a shared state. I might want to say, allow me to access this memory block, this cache block, in a shared state, or provide me a modified state, or so these are to read from this. Now, if I want to get rid of a memory block in my cache, let's say, because cache is very limited, so let's say you had a certain memory in your cache and you're done with it, you want to cache something else, so you want to throw it away. So then you throw it away, either you had it in a shared state, you say, now I don't want it anymore in shared state, or you had it in exclusive state and you say, I don't want it anymore, or you had it in owned state and you don't want it anymore, so you say put, or you had it in modified state and you say, I don't want it anymore. So these are other examples, right? So these are for obtaining them, these are for getting rid of them, and you could have requests like this to upgrade. So for example, if you had it in read only and then you issue an upgrade, then you will have access to it in modified or shared, right? Sorry, if you had it in shared and you request upgrade, maybe that means that you want it now in modified. Okay, so these are examples, right? And again, not all cache coherence protocols have all of these, depending on what the states are supported in that cache coherency protocol. Some or all or more of these requests are supported. So again, these are examples. Now, let's look at one particular cache coherency protocol. So actually, let's first look at two categories of cache coherency protocols. There is one category that is called a snooping cache coherence protocols. So with this one, if you remember about that interconnect that I said, everybody listens to every message, every request that are sent on that interconnect. So everybody is snooping on all the requests. So when a request is sent by one cache controller, it's received by everybody. So this is called a snooping. So everybody sends messages to everyone because everybody is listening to the same shared bus. Now, obviously, the snooping comes from the fact that everybody is listening to the same bus. One example of such protocols is this MSI protocol that I mentioned previously. So this is a protocol that uses only 3 states. Now let's look at how it works. So it only supports modify the state, share the state, and invalid state. So any cache controller has a cache block cached in its private cache, and it only has one of these 3 states. So it's either invalid or shared or modified. Now, MSI implements these transitioning from the states. So if you issue a load, if your CPU issues a load, then your cache controller sends a get S. Give me this location as shared because I just want to read. So this is issued and everybody receives it. And if you get an acknowledgement, then you go to shared state. Now you have this, it was initially invalid. Now you bring the data to your memory, to your cache, and you make the state of it to be shared from invalid. Now, as long as you issue loads, you should be fine. So you don't need to do anything because you have it in shared state. So your cache controller doesn't need to send any message to anyone because you have it in shared and you're just reading. If others send get S, again, you don't need to do anything. So if you're snooping on the bus and you hear some other cache controller sending get S, you're like, okay, sure. I'm not going to do anything because others also want this in shared state. So I'm fine because I'm also having it in shared. So all is good. Now, the moment you issue a store, your CPU issues a store, then your cache controller is going to send a message to everyone saying, I want this in modified state. So you're going to issue a get modified to everyone. So you issue that. Let's assume that you receive an acknowledgement that now you have it. So you then change the state from shared to modified. Now at this point, as long as you issue loads and stores, you don't need to do anything because you have access to this in a modified state. You can read and write from it. Now, let's look at conditions that so far I have just looked at the requests that are issued by me, kind of, loads and stores. Now, let's say that I wasn't invalid and I wanted to store something. So I didn't have that memory location cached and I just wanted to store something. What I could do is to just issue a get M right away from I issue a get M and I tell everybody that I want this in an M state and I get it. Once I get the acknowledgement, I go to M and I can read and write from it. Now, let's say I had this cache in modified state, meaning that I was reading and writing. Now, let's say I I'm snooping on the bus and I hear somebody says, get S, give it to me in S. Now, what I have to be doing is I have to make sure that this data is whatever I modified is delivered to whoever wants this now in memory in S mode. So that's the first thing I have to do. So that will happen through the cache coherency protocol. But I also need to change the state now, because now this is the end of the interval where I'm the only writer. And now we're going to start another interval that people can read, me included. So I go from M to shared. And I also have to make sure that the data that I have is propagated to that other CPU that wants it in S. Now, if I'm in S and I want to get rid of this, so I don't want anymore to keep this cache block in my cache, I want to free some space to bring something else, then I issue an eviction, or I just evict it. I don't need to. Actually, in this one, I don't need to issue any request to the cache coherency. I can just get rid of it. If I had it in shared and I no longer want it, I just throw it away. I don't need to issue any request to the cache coherency protocol. If, however, I'm not going to evict it, but somebody else wants it in get M. So let's say I had it in shared, and then I'm snooping and I hear somebody says get M. So they want to modify. So at this point, there is no point for me to keep this in S state, because they're going to modify it. So I'm going to make it invalid. If somebody else wants to write, then I'm going to make it invalid. So these are the two situations you go from S to I. And another way to go from M to I is either you want to get rid of it. So in that case, you issue a put M. You say, I had it in M. Now I want to get rid of it. Now you have to tell others that you're going to do this. And this is important. In shared, you didn't need to tell anyone because you had it in read only. So if you want to get rid of it, nobody needs to know. However, if you had it in M, so you have modified it, you have to tell others that I'm getting rid of it because they might need to know. So you issue a put M. You could also go from M to invalid if you hear others want it in M. So you had it in M, now somebody else wants it in M, so you go from modify to invalid. Okay, so we looked at this MSI protocol, very high level, scratching the surface. And this was an example of a snooping cache coherence protocol. So everybody was receiving all the messages. All the messages were broadcasted to everyone. Now, this has limitations. So snooping protocols have limitations. In particular, because everybody is listening to the same bus, this bus becomes kind of like a bottleneck. And managing this bus, who can send messages on the bus, who has access to the bus, is basically pain in your back. So anybody who has done any electrical engineering should know that having these shared wires between multiple controllers is nightmare. So as a result, this design does not scale well. So as far as I know, and the last time I checked, the largest snooping protocol that was implemented in a multiprocessor was for a case that there were 128 CPUs. So this was kind of the limit of how many processors this could support. And as you might imagine, this is too much. Like making 128 CPUs share the same bus is very painful. So this is kind of like the limit. But if you look at new systems that come every day, they might have more than this, many cores. So an alternative to snooping protocols where all messages were broadcasted to everyone is directory-based cache coherence protocols. So in this one, instead of broadcasting all these messages on a shared bus, you send direct messages to the owners of each block, usually. So usually there are these directories. So these are kind of like DNS servers. You go there if you have an address. So you want a memory location. You go to the DNS. Like in the DNS server, you have an address. You go there, and then you get the IP address for this website that you want to go, and then you connect to that IP address. With directory-based cache coherence protocols, you have a memory address. You go to the directory. Directory gives you the address of the owner who owns this memory right now. It could be the directory owns it, or it could be some other processor owns it, or it could be the memory owns it. Depends. So you get who owns this memory, and then you start communicating with the owner to read or write. So with directory-based cache coherence protocols, you move from these broadcasts to direct messages. So therefore, you can actually scale your design. So you can support more than like 120 processors. Now, the downside, I don't know if I have it here as the downside, is probably you will end up sending and receiving more messages, as you can imagine. So previously you were just sending a single message on the bus and everybody would hear. Now you probably have to send a message to the directory, get a message back, and then start communicating with another one, and then get a message back, and so on and so forth. So you might end up exchanging more messages. So the trade-off is now it's more scalable, but you might end up having to send and receive a lot of messages. I'm not going to go deeper than this, so I'm going to leave it at this. However, we'll come back to this cache coherency protocol very soon in the coming either today or next lecture, which is tomorrow. You will see that this could cause us a lot of problems. So having to make sure that caches are coherent is going to be expensive in a multiprocessor. No matter what kind of cache coherency protocol you use, a single load or single store could end up being a nightmare in your cache coherency protocol. There might be a lot of messages being handed over, and that makes life a lot harder than it should be. Okay, so I'm going to move on. So we talked actually about sequential consistency. So these should be, so here I'm comparing consistency and coherence. So if you remember, we talked about about memory consistency. Now you might say, what's the difference between memory consistency and cache coherence? The answer is, with cache coherence, we're looking at a single address, and we want this to be coherent on all caches. So it's about a single address. Basically for any address, we want it to be coherent among caches. With memory consistency, we're looking at different requests, loads, and stores, and we're talking about the order of these. So these are two different problems. And again, I leave it at that. So coherence concerns only one memory location. So it's about a specific memory location. And for all memory locations, we want to have coherence. Now with memory consistency, we care about the ordering of requests. So these are two different problems. Okay, so we talked about sequential consistency previously. We also talked about x86 consistency. So I'm going to move on from these. Now, I'm sort of done with the overview of multiprocessors. So to just summarize, we talked about heterogeneity in multiprocessors. We talked about the second thing that we talked about was I'm reminding myself. So coherent. Sorry, I have to remind myself. I'm losing my memory, unfortunately. Yeah. So we talked about numa next. So numa was the second topic that we covered. The third topic was caches, and the fourth topic was cache coherency. So we talked about these four, and now we're kind of ready to go back to see how these could impact us and impact our systems. So somebody is asking, what's an example of memory inconsistency? Right. So for example, you set your consistency, you say, I want to implement sequential consistency. And if that's your memory consistency model, then you better issue requests in the same order that the programmer wanted. So if a store is reordered by a load that comes afterwards or before it, then you have memory inconsistency because you went against your consistency model. So that's how you could have memory inconsistency, that you set your memory, and this is important, right? So whatever system that you're using, you have to know what memory consistency model it has. Does it support sequential consistency, or does it support x86 consistency, or does it support other types of consistencies? Because consistency is basically an agreement between the programmer and the hardware. The hardware tells you that I'm going to reorder this way, or I'm not going to reorder at all, or I'm going to reorder just stores after reads, or I'm going to reorder reads after writes. So whatever that agreement is, programmers start coding based on that agreement. If I know, for example, if I'm writing a program for x86, I have to know that loads and stores could be reordered by the hardware, and I have to code based on that. This basically brings the example that we saw with double locking, double lock checking, if you remember. Sorry, double checking, double checked locking. So if you go back to the to multi-threaded kernel slides, I had these examples where the fact that the instructions were reordered would impact the correctness of my program. So I need to know what kind of consistency my hardware is providing. Okay. Now, let's talk about multi-threading on a multiprocessor. So does multi-threading always guarantee performance? That's a question. And the answer is not necessarily, actually. So as we saw, there are some overheads when we have multi-processors. For example, the overhead of making caches coherent. That is one. The other overhead is basically creating or deleting the threads. The other overhead is context switching between threads. So there are many overheads that have to be considered. So when you have a multi-threaded application, doesn't necessarily mean that your application is faster than if you implemented it as a single-threaded application. it might well be that a single-threaded application would have better performance than a multi-threaded version of the same application because of all these overheads. The other thing that could impact the performance of your application, a multi-threaded application, other than the overheads, is basically the lock contention. So if you have a lot of critical sections and only one thread can execute the critical section, and you have thousands of threads, then you might not actually get a lot out of it, because although you have 1,000 threads, only one of them at any given time can execute the critical section. Let's say that all of your threads, all they are going to do is to do something in their critical section. So this critical section is a big one, and every thread has to do it. Now, having 1,000 threads is not going to improve your performance, because each one of them at any given time is going to run. The rest of them are going to wait. So you could potentially make it sequential. So you can just write one thread that does whatever these threads wanted to do sequentially, and that might be even better. So lock contention is another thing that could degrade the performance of your application and might not give you the performance that you're expecting from a multi-threaded application. The last one is this communication of shared data. So this is where I talked about cache coherency. So this is a subset of the overheads, the communication overhead for shared data. So we're actually going to dive a little bit deeper into this and see examples of this becoming an issue, and we're going to talk about solutions to address it. And this one in particular, in the project that I was talking about in the previous lecture, so I talked about this project that I was doing with my grad student, and we were implementing this scheduling policy. We had a flag. Each thread had a flag, and they would communicate with each other through their flags. And we got to a point where our program was really, really slow, and we didn't get why the program was very slow. And turned out that the reason it was very slow was cache coherency. So because of do I have it? Yeah. Because of false sharing, our program was immensely slow. Now, what is false sharing? False sharing is, again, a subset of communication overhead. So when I was talking about cache coherency, I kept using this notion of cache blocks, right? So I was saying blocks, blocks, blocks. What is a block? Now, a block is basically a bunch of bytes. So your block could be a single byte, but that's usually not the case in systems. In modern systems, a block could be 64 bytes or some kilobytes, depending on your system. So you're gonna, like, if this is your memory, and these are different bytes, you're gonna group them together and call this a block. And this block could become a unit of cache. So when you cache something, you might want to cache the entire block instead of single bytes. You might cache the entire block. Now, if you have a single byte here, this was our flags in the example that I said. So you have a single byte that you own, right? And nobody else owns. And then you have a byte that is shared. So this is a byte that everybody needs. But then inside that block, you have a flag that you own. It's just for you. So because I have this notion of block, this flag will also be passed like a ping pong around every time I want to access this shared data, because the cache coherency protocol or cache coherence protocol is going to treat memory blocks or cache blocks. It's not going to care about each individual byte. Now, if you're not careful or you're unlucky and one of these bytes is shared data and the other byte is for you and not shared, the byte that is not shared is going to be treated as shared, because if all CPUs want to write to this data, they're going to have access to the entire block. They're going to acquire this block as shared or modified or invalid. So they're not going to go and do it per byte. They're going to do it per block. Now, this would be a problem. And this is called false sharing, because in reality, you really don't want to share this flag. It's for you. You shouldn't pay a cost for accessing this flag because it's local to each CPU or thread. But because it's packed with other data that are shared, it's going to be passed around in different caches. And that could degrade your performance dramatically. Like, I think in our case, it was more than 100 times slower. And to deal with this, we kind of had to, so let's say we had, I don't know, we had, I think 64 threads. So we were doing this flag 64. So, and this was a character. So then all of these flags would be put in the same block. And although each thread has its own flag, so if you're thread I, you wanted to look at flag I. So this was your data and it wasn't shared. But because all of them were put in a single block, then whenever you wanted to access your own flag, the cache coherency would think that all these different threads are trying to access the same block. So that would really downgrade our performance. The way to solve it, and the way we solved it, was something like this: flag of 64 times like a big number, like let's say 248. So this way, and then wherever you wanted to access your own flag, you would do flag I times 248. So this way, we put these flags in different blocks. So now that you access this, you're going to access a block that nobody else is going to access. So this would avoid false sharing. So this is a great example to provide. And again, as I said, this implementation was more than 100 times slower than this implementation. So a very simple thing that might not be, and it took us a while to figure this out, that false sharing was happening in our system, but it was downgrading the performance of our system dramatically. Okay, so let's move on. Now, so here I talked about bunch of things that could downgrade the performance of your system. Let's talk about how we can kind of alleviate that. The first one is to reduce lock contention. So if you have these multi-threaded applications that all of them have to run this critical section, so you have this big critical section that everybody has to run, one thing you could do to avoid lock contention is to divide your critical section into smaller critical sections. So basically what this means is you can have fine-grained locking. So this is an example. So let's say, instead of locking your entire database, lock a few tables, right? Or instead of locking your entire table, lock certain rows. So that allows multiple threads to access the database, or that could allow multiple threads access the table. So instead of having this big lock on the entire database or on the entire table, have this fine-grained locking. Just lock what you really need. That way, that allows more parallelism. You can have more threads running at the same time. The other thing that you could do is to do per processor division of your data. So this, for example, is, if we're talking about heap, heap is a shared resource for all threads because all of them have access to the same heap. Now, if you have these, all threads are doing new, calling the alloc to get some data, you could divide your heap into different partitions and make each core allocate memory from its own partition. Because when you're implementing alloc, so in lab 1 you implemented alloc, but then you had a uniprocessor, so there was only one thread that was calling alloc. Now assume that you have a multiprocessor and different threads could call alloc. Now you probably want to put some locks so that, because you're allocating memory, so if if one of your threads gets allocated some memory and the other thread simultaneously looks at the heap and thinks that this region is free, then you might end up allocating the same memory region to two different pointers, and that's bad. So you want to lock it. Now, instead of having a single lock on your entire heap, you can divide your heap into different partitions and make each core and assign each partition to each core. So if your thread is running on core 2, then it gets allocated a memory from partition 2. If your thread is running on core 5, it's going to get allocated a memory that is in partition 5. This way you can actually you can avoid lock contention, and that allows more parallelism. The other one is to just forget about locks and go with the design that doesn't need a lock, right? If you remember, I actually don't know if you guys covered this programming paradigm in ECE 252, but instead of having shared data, you could assign each data to a single thread and then have message passing. So basically, it's called actor model. So each thread is in charge of a single data, and threads communicate with each other through messages. So if you want a data that is owned by another thread, you send them a message and you say, give me data. So for example, in a bounded buffer, where you have producers and consumers, you can put a single thread in charge of the bounded buffer. Instead of allowing different threads to lock the bounded buffer in queue or dequeue, you can ask this thread that is in charge of the bounded buffer to give you data or to put data in the buffer. So you just send messages to this thread. You communicate with this thread through message passing. So this is one example. For example, here, all the requests come to this master thread. A master thread creates different requests for, let's say this is a web application. Now I have a pool of threads. each one of them gets a message and deals with that message. And here the same. So there is no contention for threads to process data, because each one of them is working on a separate request. Okay, so that's another thing that we can be doing. So basically, instead of having shared data, we can have message passing. So threads communicate with each other through messages, and there is no sharing of data. I'm over time, so I have to stop here. Next lecture tomorrow, I'll talk about what if I've done all of this. I've done all the techniques that I could, but I'm still, experiencing a slowdown in my multiprocessor running multi-threaded applications. So there are more things that you could do. In particular, we're going to talk about 2 types of locks that we can use. So I'm going to end this lecture. I have another question, so I will answer that question. But that's it for today. So tomorrow we'll continue from here, and hopefully I finish this and I start talking about real-time systems. Okay, let me look at this question. I'm still a little confused about the definition of the owned state. It's defined as both read-only and dirty. But my understanding of dirty is that okay, let me go to the beginning, see if I can answer this question. So here, so if you're asking about, I'm really not clear on what is being asked, but if you're asking about this guy, it says own, read only, owned, dirty. So it means that if you own a cache block, it could be read only, it could be so it could be dirty, or it could be just owned. So it's talking about these different states that you could have. So it says owned if you have a cache state in the state of owned, that could be read only, it could be owned, and it could be dirty. So it could be any of these, right? I'm not sure if that's what you're asking, because I think the best way to deal with this is for you to come to the office hours. So I'm still not following your question. Okay, thank you so much for sticking around. Thank you for those of you who are watching this the recording. Take care, be safe, and talk to you tomorrow. Bye-bye.